Good morning, everyone. Sorry for the late start. My computer decided to just act all weird today. But fortunately, after a reboot, I was able to get back online. So let's see here. Who do we have today? Just act all weird today. Just a moment. I got to kill my other computer here. So we have James Keene. We have Alistair. We have Ian. And
morning, everybody.
Another copy of Ian. We have two Ians here today.
Oh, I must have logged in twice. There's an echo there.
Can we keep you like that? That's cool.
See, can I get rid of one of them?
Yeah, you cloned yourself and you sound like God. Okay, so let's see here. Actually, I can kick your clone off is what I'm going to do. There we go. Okay, there. I got rid of your clone, Ian.
Thank you, Franklin.
There we go. So, let's see here.
I don't seem to be in, though, at all. So,
Pardon?
I don't seem to be in from my vantage point, though. All I can see is the homepage of StreamYard.
Well, we do see you. We do hear you. So, do you see us?
No.
So you can't see like our screen, like if I share something.
No.
Ian, you should probably disconnect and know you're disconnected. Franklin, get rid of any other Ian.
Are you sure it was the clone that was kicked off?
Well,
yeah,
the clone seemed to
be original.
Right? Maybe I'll just log it out and log in again completely.
Yeah, probably is what you should do.
Yeah.
Well, wait, you're clear now, Ian.
So we'll wait for, let's see here. Okay, good. I see James is still moving. So in his other, well, I'm going to add that version of Ian. There's still another Ian.
There's no echo now, though.
There's no echo. Okay, well, we'll just leave your clone there, and we'll get on with the conference. Great. There's always so many adventures with all this online stuff. Is it raining in your place, James?
Or is that sound that you just heard was something on my roof. I'm not sure what it is. It could have been a large iguana.
Yeah, it could have been. Yeah, there's something because you live in a metal tinned house there, right? And when it rains, we will not be able to.
It's got a shake corrugated roof.
Yeah, shake corrugated roof. Okay.
And all right. Very loud sound.
Yeah.
So, did you guys have any particular topics you might be interested in? Let's see here. I got a what I wanted to talk about is I had gotten a basically a video response from Draft Science, and he put up an interesting video about his response to polarization. So he had some interesting points. So I wanted to see whether we could go over that. Let me see if I can bring that up. See whether you can at all see or hear this. Okay. So I'm going to go full screen on that. Let's see here. Now I can't control. Just a moment here. So I got that. Let me share the screen. Share audio. Okay. All right, so I want to see whether you can see and hear this.
Response to Franklin who seems responsive to responses, so that's good. Try to spare him, make it as brief as possible, the important.
Okay, can you guys hear that?
Yes, it was a little low, but we could hear it. I could hear it.
Okay, so like I said, he said that I'm responsive to his responses, so I'm responding. So, which I am. So, I kind of like this guy, Draft Science. He's got a pretty big following, and David, if you're watching this, I think we should definitely unban him. We should, if he wants to come on our science chat, I would welcome him to do that. But let's see here. Let's go back and see this video. So
if you can, Franklin, zoom in on the
okay,
video.
well, we can make it bigger. How about that?
Yeah.
So the screen here, he's got this thing where he can put my video on like the left side, and he can talk with a whiteboard on the right side. So that's pretty cool. I can't do that. All I can do is share my screen. But this is in response to an explanation of polarization that I did. Now, we're not going to go over the whole hour and a half. So I think I'm going to, since I watched this before, I think I'm going to try and cut to the chase here.
Points to start with anyway, and then I can drag on later, play some of this all the mechanism.
Let's see here. Let's get to when he starts actually drawing some pictures. Okay.
This basic frequency. So you have this basic.
I can see nothing. I can only see your picture, Franklin. I can hear him, but I can't see anything.
You can hear him? How
Yes.
is it you can only see, what, do you see my live picture or do you see the YouTube?
I see your live picture.
Oh, you see my live picture?
I did see the YouTube when you put it up a few moments ago, but not now.
Well, let's see here. If you see that, just let me know. I'm going to share the screen again. Okay. Now,
Right.
hopefully you
Come
can
up now.
see it. Now you can see the YouTube?
Yes.
Okay.
I can see both your picture and his.
All right. So let's get to the
Just
basic
change
differences
how many of these are
in
on, off.
the way
Put music
Draft
on.
Science sees the world and the way that I see the world, and what are the differences. So you see he is drawing the world, and he's using circles, and these circles represent photons, okay? Now, if you guys have any questions or comments, we can stop anytime and let me know. But his world is built on photons. So draft physics, if I'm wrong about that, let me know. But I think that this is the basic fundamental building block of his hypothesis. Now, this is different than my hypothesis, which is that basically the photon is a wave phenomenon. So the big difference here is that draft physics does not believe at all in any kind of wave phenomenon. So he seems to be taking the opposite stance, which is that photons are strictly particle phenomenon. So this fundamentally, the fundamental difference has to do with this: is light a particle? Is light a wave? Or if you're like the mainstream, think that it's both, depending on what you're looking at it with. So I think that in some ways he's not wrong, but I would say that to draft physics, that the main problem here is that his hypothesis is fundamentally incomplete, because it requires the existence of the photon that he's representing by his little circles here. Now, it's possible that, the photons actually physically exist like that, and that they are a particle. It's just that we've never ever actually, found the, photon as a particle that we stick into a thing. Like it's not as well known as, say, an electron or a proton or a neutron. In some ways, the particle, the photon, does actually exist in like the standard model of physics, as a particle. So, there's certainly a lot of things to indicate that it could be treated like one. I mean, I think this is kind of his point, that, if it quacks like a duck, waddles like a duck, looks like a duck, it must be a duck. And so if you have a photon and it looks like a particle, acts like a particle, well, it must be a particle. And that's his basic stance. But my argument against that, and an argument against most dissident theories that start out this way, is that you are starting with something that is like a little green fairy, which is that it's a completely made up thing. I mean, and a lot of theories do start up there, like Alistair's got his ether particle ball, and that once again could exist just like draft physics' photon. And there's basically, unfortunately, no way to disprove or prove that. And certainly, that it holds together logically is still not sufficient to prove anything. I had the analogy of, if you have your socks disappearing out of your dryer, you can hypothesize that little elves are coming and stealing them while your clothes are drying. Right now, in the absence of any experiments, there's no way to disprove that. But yet, it is completely logically consistent that that happens. So logical consistency is certainly grossly insufficient for determining the truth of the matter. So, like I said, the biggest downfall of this photon model that draft physics is purporting is that you have to basically postulate the existence of this photon, okay? And it doesn't have any relationship to anything else that we know. I mean, it's not something that has anything to do with electrons or neutrons or protons or any of the other particles that we know about. That it's something which has to act completely uniquely, right? It's its own thing. So, and I think that that is just a completely kind of a made up thing. Well, actually, it's not made up, because this is kind of where I think that he's on the right track. But the question is, the main criticism is, what is your photon? What is that little circle that you've drawn there on the screen?
Could we criticize the dude after we watch him?
Well, it would take like an hour, 15 minutes to watch the whole thing. So, but you can feel free to go and watch him. If you look up draftphysics.com, you can go watch all his videos, and you can do that in detail. So I'll try and bring up, the relevant points as I kind of see him. I kind of skip through his video. But, if you have any comments or criticisms, feel free to jump in at any time. I mean, if you think that light is a particle, then, let's talk about that. I personally don't think it is. But I'm thinking that, he's not wrong in the sense that he considers light coming in as, clumps, because that's the terminology he uses. He says, light is like a clump. And I would agree with him, but it's an incomplete picture. So the main criticism is that we don't know what his photon is made out of. Now, to answer that, I would say that that clump does exist in, say, my hypothesis. My hypothesis, which uses waves. So it's like my theory goes one level deeper than his theory to explain what that photon clump actually is. So I would say, yes, you're right to treat photons as little clumps. You can, in fact, generally correctly draw them as distinct circles because they do travel through space as a distinct entity with distinct volume and length and dimension. So you could describe it like that. Now, if you look carefully in his picture here, he's got some little markings inside of his photons, and that is trying to represent the polarization angle of each photon. So I think he's kind of got them cross-hatched in different directions, showing what are the possible different polarizations. And he says that the polarization is an inherent part of that photon. And once again, I would agree with that. But the thing is that that photon is actually a wave phenomenon. So that's why I've been kind of pushing this new concept of what a photon, what the shape of the photon actually is, which is, I said that a photon looks like a rod. It's like a rod that travels through space, and the direction that it's turned kind of represents the polarization angle. So that's would be very similar to what draft physics has, which is, his photon is like a circle. And if you consider that the photon could take any 360 degree, my rod can take any of 360 degree in a circle, then you could in fact say that, it's in fact kind of circular, even though, it's a rod, but it can take any of those positions. But the space that it could potentially occupy is like a cylinder kind of thing. But like I said, but he's kind of blinded by the fact that he thinks that all phenomena, including radio waves, travel like this. So the other difference is that I don't think that radio waves travel like that or look like this. What he's describing is what happens purely in electron-generated light, like visible light, any kind of light which is generated by electrons smashing into each other or something like that, versus radio waves, because radio waves are a very, very different animal. Let's see if we can go forward a bit here.
So this would be but the basic carrier signal is made out of real stuff, and obviously you receive an amount of the real stuff, but the only varying part, the carrier, doesn't vary. The carrier is clearly on and off, in my opinion. And so he's going to use an oscilloscope as an argument. And
so as you can see, he's talking about his photons as being basically real stuff, but he also mentions that there is a carrier. Now, I'm not exactly sure what he means by that, because if you think light is a particle, then it really doesn't need a carrier. Like I can throw a rock across the room and it doesn't need any other medium for it to transfer its kinetic energy to the wall that I'm putting. That is different than, say, sound wave, which does require a carrier. And there is no physical particle actually moving from one side of the room to the other in that case. There's just a compression wave that travels from one side of the room to the other. So I'm not 100% sure whether his photon particles do actually physically travel from one side of the room to the other, like they were little BB balls, or whether he still thinks there might be some sort of carrier, in which case he would have to be talking about a wave. So since he's so anti-wave, I'm just going to have to think that he thinks that it travels across the room like a BB, like a literal particle. And the point he's trying to make here is that when these little BBs hit something, like an electron, they just create a spike in the whatever the receiving object happens to be. And he makes the point that what these photons do is that they impact electrons and they cause them to move, which I would also 100% agree with. It's like, yeah, that's what happens. Whatever these waves are, we detect them by their activity upon electrons. They seem to cause electrons to jiggle around at whatever these things are. But he's trying to argue that since these things come in such a quantized state, that there is actually no gradual sinusoidal wave kind of activity. That if you were to look at carefully, it'd be like listening to hailstones hitting your roof, right? It'd be individual, bangs, right, like that. And the only reason why we see the sinusoidal effects is that it's just being kind of smoothed out, or he calls it noise, right? That the only thing that really matters is the individual hits coming into, say, the antenna, and what anything we see outside, anything we see in the circuit is just kind of being smoothed over. And that he's not convinced by, if you hook an oscilloscope up to a radio receiver antenna and you look at that, you can see the voltage, and that's all the oscilloscope is doing. It's just measuring the voltage, and you can just see it varying over time. I mean, I suppose you could just connect a conventional voltmeter up to an antenna and you would see the needle wave back and forth. It's another way. So it's not anything necessarily to do with the oscilloscope, because he starts talking about how the oscilloscope takes and how the trace works, but all it's really doing is just measuring the voltage, and we can clearly see that there's an oscillating voltage at the receiving antenna, and he's just not convinced that shows that there's a wave. And once again, I believe that is because he's kind of blinded by the fact that he thinks that all radio or light phenomenon are the same. And so he has to, when it comes to things like radio waves, he has to still bucketize his thinking into these photon buckets. But, a point I was trying to make last time is that radio waves and light waves are two different animals. They are generated in a different manner, and they propagate in a different way. That does actually allow for the smooth sinusoidal expressions of these waves. So one counterexample I would say to draft physics is that the shape of that wave that you're receiving, that's not noise. Now, I haven't exactly done this experiment, but I'm pretty sure it's true that you can take your transmitter, your radio transmitter, and you can broadcast different wave forms. You can transmit a nice sinusoidal wave, Or you could transmit like a square wave, which is just on-off pulses, or you could transmit a triangle wave, which is, not sinusoidal, but straight 45-degree angle kind of rise, because the rises are different. The shapes of those waves are definitely different, and you can be distinguished from each other. Now, I'm saying that if you were to look in the receiving antenna, you would recover those exact same waveforms. So if you transmitted a triangle waveform, you would see a very different waveform compared to if you were transmitting a sine wave waveform, or if you transmitted a square wave, you would see a very, very different kind of thing. Now, if draft physics is correct, then it wouldn't matter the shape of the wave that I'm transmitting at my transmitter. The only thing that would really matter would be just the frequency, because in his mind, that when you're transmitting, you're sending literally these BBs across space, and the only difference between these BBs is the amount of space between them. And the only thing that matters is the frequency. So if draft physics is right, that no matter what I transmit over, whatever the waveform I transmit, it's going to be received as a sine wave, pretty much. But I don't believe that's the case. I believe that the radio waves will be received in exactly the same shape as they're transmitted in. Now, once again, I haven't done the experiment, but I'm pretty sure that that's the way radio waves travel. So that is one very large counterexample to what draft physics is saying. And I'm saying that the only reason why he needs to say this is because he's stuck in this idea that radio waves are transmitted the same as light waves. And I'm saying that that's not true. Once again, my theory goes one level below his to explain that radio waves are just like sound pressure waves, and that they are sent out as, very, very large waves that spread out, like you throw a rock in a pond, you see the waves spread out. That is how a radio wave travels. Now, we really don't have any analogy for how things like that travel as a specific photon. I was thinking about this, and it's like the only analogy that I can possibly think of, and I hate to use this analogy because I hate toroids, but if you've seen these Vortex Guns, they send out like this toroid, like smoke ring, right? And photons would be kind of like that, in that they maintain their shape. And, you can use these Vortex Guns. I've seen them at science centers, and you can fire them, and like 100 feet away, they will hit a specific target. They don't spread out. They occupy a very specific volume. And I'm saying that that's really the only kind of analogy that I can kind of point out to show what a photon might travel like. But, that's a very, very bad analogy. I'm thinking that I'm saying that the photon travels as a rod. So if you could just like ignore that whole toroid part and just imagine that this cannon fires out this like cylindrical puff of smoke, and that cylindrical puff of smoke doesn't spread out, but yet maintains a very, very specific shape of a rod, and you could imagine it has some kind of orientation relative to its direction of travel, and that controls its polarization. And that thing is what draft physics is talking about in his pictures here, because those things absolutely will travel like that, right? So I think anything that he has to say about the activity of photons is actually correct. So let's go in a little bit further here. And he's making a point here about which I think is
right.
correct.
Even if you think of it as a wave, it still works as understanding here's a bump, here's a bump, here's a bump. The bumps are what's pushing. Okay, so the idea would be is you're trying to have an effect. And so we shoot photons at this, and we observe that, you know, photons are going like this versus photons going like this. Okay, so we compare these two and say, what's their effect on this thing in the spring? Well, these slow ones, the ones with hubs far away from each other, intensities, I would just say photon bits. Okay, they hit it and they compress the spring, but the spring springs back, okay, because of the time problem here. There's too much time. It hits it, it lets it relax, and then it hits it, and then it lets it relax. So it just ends up going back and forth and back and forth and back and forth. Now, when you get up to a certain kind of intensity, all right, then you're starting to not get any, you know, you're reducing the amount of recoil. So now, if you take this ultraviolet light, all right, and you shoot that at it, all right, you'll hit the electron this far, the first hit, and then it doesn't rebound very much, only a little bit, and then it gets hit again, it goes forward some more, and then it gets hit again, it goes forward some more, and you get the idea that now it can get to the hole, and it can fall through the hole. And this is what we saw it, but this is seeing, okay? All right, we see an event, we see an effect.
So here, Draft Science is explaining how the photoelectric effect works. And I believe, you know, I totally actually agree with this what he's saying, in that, you know, the light is coming in specific packets. So he thinks it comes in, you know, a clump, and and that does agree with my model in that, you know, it is kind of a clump. It's a specific thing, but it's made out of a wave, in my opinion. It's a compression wave phenomenon, and it's not an actual particle that he thinks it is. But, you know, it acts exactly the same. And the main point that both he and I are making is that the reason why the photoelectric effect works the way that it is that it's just not delivering enough energy per unit time in order to trigger the event that we see, which is an electron getting kicked out of the surface. Now, I don't think, you know, he's using the analogy of it falling into like a hole and that coming out, and it's like, well, you know, that's an interesting analogy. I don't think it actually works that way, but for the purposes of our discussion, you know, that's probably, you know, fine, I suppose. I don't think it really works. I think it's more like if you take a tree and you shake it and it's got plums on it, that you have to reach a certain frequency before there's enough energy available for the plums to fly off the tree. And it's be more like that. And that but the main idea is that light comes in these specific packets, these quanta, and in order to release an electron, you have to just put more of those packets in per unit time to add enough energy to the electron to get it to eject. And it's important to say that each of these, you know, light photons contains the same amount of energy. That it as a, you know, as even as a wave phenomenon, that would mean that the amplitude is fixed, and that every single light photon you have ever seen contains actually, you know, basically the Planck amount of energy. I mean, the formula is E equals Planck constant times, you know, frequency is how they express the amount of energy in light. And that expresses that the only thing difference here is just frequency. So the more of these things you send at something, the more energy it's gonna absorb per unit time. So, like I said, I would agree with that, but I don't think that this is the mechanism by which radio waves are received. I would say that Radio waves are different in that they can actually take on a variable amplitude versus light phenomenon, which only has fixed quanta because it's being generated by something which is quantized, which is electrons, and electrons are quantized in space, and therefore they can only generate a fixed amount of energy, like a fixed quantized amount of energy. But I think a radio wave, if you've got a radio transmitter and you transmit exactly the same frequency, like a 60 hertz signal, and you transmit it with 1 watt, you can receive that and you can see how much power that is. But now if I turned up my radio transmitter to 10 watts and didn't change anything, then I would see that the amplitude on my receiver would also increase by 10 times, right? So definitely the wave can take on variable amounts of power. And I would predict that if we could possibly create a radio transmitter that works at visible light frequencies, we would see that the photoelectric effect doesn't actually work anymore. Because if that were true, then let's say we take like some green light, and normally with the photoelectric effect, it doesn't matter how bright that green light is, it just never has enough power to eject the electron, because each of these photons only has a certain amount of energy, and turning up the brightness does not deliver any more electrons and any more of these photons to the energy to the photons. Even if you send more of them, they're still too spaced out in order to put enough energy to eject it. But if you were to be able to create a radio wave at light frequencies, then all you would have to do is turn up the amplitude, and at some point you would get enough energy to eject the electron with even a single photon. You could put enough energy to eject it with just a single photon. So that would vary with the amplitude, because what we're doing in the photoelectric effect is we're confusing that amplitude with just the sheer volume of incoming photons, right? It's not the same thing. They're thinking that when they turn the light up, that they're increasing the amplitude, but actually they're not. They are not increasing the amplitude in any sense. But I think, like I said, the main point here with draft physics is I totally agree that this is the way that it works. And to the extent that your clumps are my rod-like waves, then we can come to agreement on that. But draft physics would have to come to the realization that there are deeper physics to what he's observing, that his photon can be explained in terms of more basic physics. And as a physicalist, this is why it's important. This is why I like waves. I like waves. Draft physics hate waves. He doesn't believe that there's any kind of waves at all. But I like waves because we can see those in the actual physical world, and we can play with them. We know how things like sound waves work. We know how waves work in water. And we all know that that's a particulate. We know that they can deliver energy, and we absolutely know that they exist. So I like waves. And draft physics is not at all convinced about the wave characteristics. He doesn't think interference shows that the waves can have that light is a wave because they can interfere with each other. And, that's kind of a difference of opinion. Now, we don't always know what interference is due to. I specifically in terms of light, it could just be that more of the photons hitting the bright spot, and they're just like fewer photons hitting the darker spots. And I think that actually in a lot of interference cases, that's actually is what's happening. Like they show interference of electrons in these slit experiments, and I don't think the electrons are interfering with each other. I just think that the edges of the slits are guiding the electrons such that more electrons hit one band versus another spot. The dark spot aren't canceled electrons. Those are just electrons not hitting that spot. So, there's an argument to be made, there, that interference is not, the greatest evidence of wave activity. But I would point out the original early experiments in radio waves, in that if you have a radio transmitter and you spread out a bunch of receivers all along the way at different distances, and you can detect where the nodes are. You can detect where the maximum amplitude reception is, and then there's a low reception distance, and then there's a high reception distance. And this was actually the experiment that, quote unquote, proved that radio waves were actually waves, right? They're not a solid particle that travels from the antenna to the receiver, because if they were, that it wouldn't have these nodes in them. You couldn't find a minima and a maxima. So that is
one wonders if there really is there. In other words, it could just be that at certain distances, radio waves bouncing off the ionosphere heighten reception at a particular point or distance from a radio station. As everybody knows, when you're driving, listening in the old days to an AM station, that this occurs, and there are hot spots where reach distance where you're getting a lot of reception from the waves bouncing off the ionosphere. If I may jump in a few comments about this draft science gentleman, it maybe in other videos he provides background, but it seems like he's firmly rooted in the continuous space-time theory era. He draws these little circles on his board. It looks like most of what I've seen so far is sort of a primitive rehash of what can be gathered from a Physics 101 textbook at the college level. And I'm not sure where there's any merit in even looking at what he has to say. But like for example, when he draws a little circle on his board there, and has a polarization vector arrow in it, if that's what that shows. I couldn't quite exactly see what's in the little circles, but if you rotate that space in the continuous space-time theory to another frame of reference, the direction of those arrows are going to change with reference to another frame of reference. So what exactly is he talking about? It's really something that's undecipherable. So maybe, as I said, to give him credit, in other videos he explains this, but just to draw a little circle on a chalkboard or a whiteboard or whatever you call it, is that where is that? Where is it in space? What is your reference frame? It's sort of like, no wonder he's on YouTube. He represents absolutely no threat to the physics.
I think that's actually a reasonable point that he's making there. So I would argue that he is saying that the photon is a clump, and that it has a physicality, and I agree to that. Now, if you're asking, what its frame of reference is, it's probably, you can take any frame of reference, and this is where you get into the whole relativity thing, that if you think that all frames of references are the same, then, everything is always relative to each other. And I just have that just That's the thing that doesn't make any sense to me. Anybody who says anything like that.
I'm not talking about relativity per se, just to clarify. I'm just talking about simple geometry. If you rotate the frame of reference, the direction in the new frame of reference of the polarization, whatever that is different. And I would like to see that has nothing to do with relativity. That just means you're rotating your frame of reference. That's Euclidean geometry.
And I'm saying that you can't do that. I mean, it's like you cannot take the frame of reference that this thing is generated and then go look at some other arbitrary frame of reference and say, aha, it went from 90 degrees to 45 degrees. It's like, no. I would say that...
Of course you can. Of course you can.
No, you can't. This is a fundamental disagreement here, in that, and to a certain extent, you have to set down what Einstein did, which is to set the stationary frame, which is you just pick one and you stick with it, right? This is the deal. You stick with the frame that you pick as stationary, right? You cannot make measurements in your stationary frame and say, okay, that angle is 45 degrees. And then go run off and say, okay, now we're going to go pick some other frame of reference. And I measured that, and that's 90 degrees. So you're saying, okay, well, then what degree is it? You know, it doesn't make any sense. Yeah, that doesn't make any sense.
That is the question. What degree is it?
What degree is it? It is the degree.
Polarization.
It is degree.
And I'm not talking about relativity in any manner, shape, or form. So to bring relativity into it, special relativity into it, is irrelevant to what I'm saying.
We're not talking about relativity. The direct answer to your question is it's the degree as measured in the original reference frame, which you have declared as the fixed standard reference experimental frame. You pick one. That's the frame, that's the angle that you measured, and you cannot legally measure it in any other frame. So whatever frame that this light was generated at, so let's say that, you know, this is the light wave that was generated and it's traveling towards you like that. Okay, so what's the degree here? So that looks like 90 degrees, right? So it's traveling through space at the 90 degree according to my laboratory frame, which is my room, and it's always going to be 90 degrees. You're not allowed to pick some other frame of reference, like, you know, if my entire room was planted at 45 degree and then say, okay, well, now it's at 45 degrees. Doing that does not make any sense. But
the laboratory frame is an arbitrary frame. I mean, what are you attributing stationary to? The frame in which the light was generated. Well, the source could be moving itself. So you could take a frame moving with the source, or you could take a frame which is stationary to the source.
The point is that you can only pick one.
Well, which one should you pick?
Any one you want, actually. It doesn't actually matter. But you have to stick with it. It's like you can't make your measurements using two lengths worth two different. It's like measuring lengths with like a foot ruler and a meter stick. It's like,
yeah, well, that's a different.
Yeah. You come out with different numbers, right? The numbers are different. What's 10 on my meter stick is totally different than the 10 on the yardstick. In order to make you know, proper measurements, you have to stick with a standard, right? This is how NASA managed to miss Mars because they confused, you know, feet with meters. They use different frames of reference. You just can't do that. Right? It's not fair.
Yes, you must be consistent. I do concede that.
You must be consistent.
But I mean, I think once you make the appropriate transformations, you could move to other frames. Now, in my view, the appropriate transformations would be Galilean. They wouldn't be Lorentz. But you must be consistent. That's certainly true.
Well, I'm just defending what draft science said, because actually that is totally what my theory says. I'm saying that what draft science says about photons is actually totally correct, in that, you know, they travel as, you know, he calls it a clump, and like I could agree with that. I could, you know, as a model of a photon, you know, this is not a bad model, that it travels I would make it more a rod, but it could actually be a sheet, but it could be a rod. The only thing it has to have is a rotational axis, right? And that's what draft science was. He drew his photons to look like that. It's a circle. It's got some line through the middle, and that represents the polarization angle, right? So photon travel could come in at any angle. But, I'm just saying it's coming in as specifically a rod, as a very, very specific hypothesis. I haven't always said that a photon travels in as a rod until I basically discovered that seems to fit the bill. But you do have to have this thing where, people have a hard time imagining, well, how does a compression wave travel like a rod, right? We don't normally see that. But that's why I tried to come up with the analogy of like these vortex guns, and even in ordinary particulate space, we can see something that travels as a pressure wave. It doesn't spread out. It can hit targets far, far away. It looks like a particle, but it actually isn't. I think probably the molecules that start out inside the vortex gun is, well, actually, that's why I hate vortex, because actually in a vortex, probably the actual molecules that started in the vortex gun actually do physically travel, because we can see the smoke molecules, and those are obviously belonging to the origin, and they have to travel all the way and hit the target. But, I'm saying that that's not, it's a horrible analogy. But if you have a hard time imagining something that travels like that, I'll just point to that and say, that kind of travels like that. You can't say that kind of thing doesn't happen, right? Because it does. Although that's, like I said, an absolutely horrible analogy. But I don't know. But Ian, what do you have any comments? Do you have any particular thoughts about whether light is the particle that he is saying that it is, or is it that, or what do you think of my hypothesis is that I'm saying that, yeah, that's totally correct. You've got that photon, it acts exactly the way you think it does, but that is actually based on wave phenomena.
Well, I'm a little hesitant to comment, as Carl suggested, maybe too much on the draft physics side, because, you've only just given snippets here and there and maybe given your own interpretation. But he seems to be making, well, probably because he doesn't accept the wave nature of electromagnetic radiation, as you say. He seems to be making a distinction between light and radio waves, which to me is just a distinction of frequency or wavelength. Now, but I think you may be as well. I'm not sure. I mean, in your analogy, Franklin, between sound and I don't know. You draw a very strong analogy between sound and, I don't know if it's light or radio waves, but you seem to make a distinction. Maybe not as strong as the distinction he makes, but you seem to make
that's a very important distinction, and that I'm saying that radio waves travel exactly the same as sound waves. Anything that you can imagine sound wave doing, I'm saying a radio wave travels that way. But, and this is the blind spot that draft science has, photons are generated as quantized packets. It's like you took a little slice of a standard sound wave, and it's like if you throw a rock into a pond and you see the waves spread out, but suppose you put like some kind of blinders or blockers on that, and you only took like this little slice of the wave, and that's the thing that actually travels out, just this tiny little slice of a wave, and that is a photon, and that wave can travel forever. pretty much. That's why we can see light from distant galaxies a billion light years away, because they can travel basically friction-free, but they're traveling as these little slices of waves, right? And I'm suggesting that there might be ways to experimentally prove that the photon is that actual shape. So, I've suggested that if it does have a finite width, that the degree of rotation around may be quantized as well, because you can't, because if it's traveling through a quantized space, that's like the pixels on your screen, and you can only draw, so many angles. It may look smooth, but at some point you look at it, it gets jaggy, right? There's some limit to the degrees, the angle you can actually draw properly. So,
but you're willing to admit of a particle nature for light transmission or something like that, but you're not willing to admit of a particulate nature for electromagnetic radiation of say lower frequency. You see that's some sort of cutoff point at light.
No, that would be, you said a couple things there I think need to be clarified, in that photons are strictly a wave phenomenon, okay? In no way is a photon like a physical BB that travels from one side of the room to the other and carries its mass with it, right? I want to make sure that's clear, that I don't believe that photons do that. And the only cutoff that actually exists is simply our ability to generate these things. It's not a property of the electromagnetic wave itself. It's just that light waves are generated by electrons bouncing up and around the vicinity of atoms, right? That's how light waves are generated. Visible light waves are generated. Versus radio waves, which are generated by just shoving voltage into a metal wire. And there's a limit to how fast we can vibrate our antenna. And I think it must be well below the frequency of visible light. Or, maybe it isn't. Maybe with sufficient technology, because I'd like to see this. I'd like to see a radio antenna, and I'd like to see it driven at optical frequencies. And so my antenna should start glowing green or red or blue or some other optical frequency color, right? I think that would be really cool. You just generate light by just using an oscillating circuit. But I don't think we can do that, right? So the cutoff is just a technological limit to how fast we can drive an antenna, right? And the technology.
Well, we have LEDs that do that. You can get green ones and red ones, and I think there's even blue ones.
But that is still being generated by electron transition. Electron transitions. You excite the material.
Well, you said you'd like to see that. You shove some voltage or electricity or charge into an object, and it puts out visible light. Well, we have that. They're called LEDs.
Yes, we do, but that's not due to what I would say a radio transmission. We're not shoving a 440 nanometer wavelength alternating frequency into the LED to cause it to generate the red light. What we're doing is we're reverse biasing a semiconductor, which is causing electrons to jump up to different energy levels that they're dropping back down. That is what generates the quantized light. And but this is a very important.
I just have a general question. First, I had more questions about draft physics than actual critiques, because my questions require answers before I can even evaluate what he's saying beyond a simple rehash of Physics 101. But my general question in several of these Saturday sessions is what is this fascination with the wave-particle duality? Why is this such a fascination in all of the discussions? It's either this or it's that. I mean, aren't waves made of like ocean waves? Aren't there particles of water, involved in those waves? In other words, I'm just, this is just a comment. There's not, or a question. What is this fascination with this duality that it's this or that? I just wonder. I'm sort of befuddled.
Well, this is
It's an interesting phenomena to look in and see this fascination taking place.
Well, you can see that difference between, say, me, Mr. Wave Guy, and Draft Physics, Mr. Particle Guy. So we seem to be at complete odds, right? He is.
Well, I don't know, Franklin, because you do speak about particles. That waves consist of particles in the ether or whatever, or at least the ether does.
Yeah. Well. For my part, maybe in answering James to a certain extent, part of the fascination might be in that modern physics conceives of this duality in a vacuum. In other words, you have particles which operate in a mediumless environment, and they also accept a wave nature of these interactions. But I mean, in classical physics, which I would adhere to in this respect, you have the duality considered in terms of a wave nature in a particulate medium. So hence the analogy you gave of, say, water waves operating in an actual medium of liquid. That's quite easy to conceive. And classically, it's fairly easy to conceive this. But the fascination is really in terms of modern physics, where the wave is operating in a vacuum, and yet it's particulate. So that might be a partial answer. I don't know.
Well, there are a number of people, including myself, who think that ordinary, what we would call perfect vacuum, that is vacuum without ions or atoms in it, is still filled with, is still teeming with quanta. In a lot of the classical 20th century quantum physics, and even up to today, I suppose, this vacuum is considered to be like a virtual sea of particles, or so-called virtual particles, and they even talk about phonons being the virtual photons, and the photons being the actual realized ones, whatever the hell that might mean. Now, so what Ian just said about we have to talk about particles in a vacuum. Well, particles, the vacuum is not nothingness. It's not empty space, according to at least my point of view. So I'm still fascinated. What is the the guy with the blonde hair can draw his little circles on a pad without explaining really anything about what the context is, where these particles are these little circles, whatever they are, and talk about them, as the video was supposedly for 1 hour without any context. There's no way to evaluate that. And no wonder he's on YouTube. He's absolutely no threat to anybody in the physics community. He's just some guy talking about physics 101. It appears.
Well, we're not any threat to physics. I would only add that it's fascinating because it can't be both, but yet mainstream says that it is, but it can't be. It's like light. If it's a particle, it's a physical thing. It travels from point A to point B, carrying whatever it is made out of. That is one way that a light photon could be, which is incompatible with the idea that a photon is a wave phenomenon, which means there must be a medium, and
But it's not incompatible.
It is incompatible.
I mean, if the wave is composed of little quanta or little particles or whatever you want to call them,
that is not. Maybe that's the problem, because that's not what they're saying.
Say it's incompatible, but
no, it is
totally incompatible.
That's not what they're saying. They're not saying that there's little particles in the waves and that's what's hitting. They would adamantly say that there is no medium, right? So therefore you can't have a wave at all. There aren't any particles in the medium to hit. It has to be travel like a bullet or a BB, right? That is the particle conception of light. And
okay, what Franklin just said, sorry to cut in, Franklin, but after all, we have to have a free-for-all here to some extent. What you just said is a very succinct, wonderful explanation of the particle idea, the no wave, but only particle idea. And obviously, it's rubbish.
Well, why would it be?
In other words, congratulations, you've just eliminated that option.
It's not rubbish.
Well said.
Because, it looks like a duck, it quacks like a duck, it must be a duck. If you look at like gamma rays, when those things are generated, when they hit the detectors, they hit a specific spot. I mean, just the same as if it was hit by an electron. Now, we agree that
everybody in conventional physics believes that the gamma ray is delivering a thing, something. It's called energy.
Yeah, and it delivers.
And so something traveled from the source of the gamma ray to the target. So what are we talking about here? Obviously, I mean, are we going to then say energy is nothing? I mean, is that where we're going here? In other words, I'm really looking for the sense of it, because obviously in any kind of a light signal and then reception situation, whether it's radio waves or anything else, something is going from the point of origin to the point of destination. And to say, well, really, no, there's nothing going. I mean,
no, they don't say that. I mean,
that we have something is going between the two points.
There's no relevance, because we're saying that gamma ray is one of two things. It's either it's like an electron. I mean, if we can all agree that electrons exist, then that's a particle. It doesn't need any medium to travel from point A to point B, and it's carrying its stuff, its electron stuff, from point A to point B, and that's how it's delivering its energy load to the target. Now, the question is, how does the gamma ray do that? Now, the gamma ray could also do that. It could also be a particle like an electron, and it carries its gamma ray stuff with it, and it doesn't need any medium, and it's going and impacting the target just the same. Or,
okay, Frank, to put these 2 points of view, which you succinctly summarized again, and you're very articulate, I must say. I hope I can be as articulate as yourself. But in the two examples that you just gave, they both agree in that something goes from point A to point B. So what's the difference? It could be that something is in somewhat of a different form or aggregate, and we're going to call it an electron or a particle, and that something is not quite so well aggregated, and we're not going to call it an electron or a particle. But it's clear in both examples that you very succinctly just summarized, something is going from point A to point B. And so what is all this talk about a dichotomy? Why are we trying to divide this up as if the two somethings are so radically different in the way we theorize or try to understand the phenomena and understand the data? End of point.
Because they are. They are.
Because they are. Well, I'm afraid that's not good enough.
They are.
Well, I think in terms of what many of us accept, there isn't a major dichotomy. It's just maybe different ways of looking at one
Here, here.
phenomenon. But from the mainstream point of view, there is. I mean, they admit there is. Because of their essential nature of the mediumless, the particle-less medium. So it's even been jocularly said that they say that it can be only analyzed in one way at a particular time, and then for another experiment it can be only analyzed in the other way. So it's been jocularly said that on Mondays, Wednesdays, and Fridays it's a particle, and on Tuesdays and Thursdays it's a wave. They see it like, I don't know who said that, but it's one of the scientists. But
Brilliant.
So they admit, they say, oh, we're completely confused that for certain experiments and on certain days we can only analyze it as a particle, and then for other experiments and on other days we can only analyze it as a wave. So we see a major difference. So I think that's really determining why we are arguing about this. But from the point of view that many of us here accept, there isn't this dichotomy. It's just maybe other ways of looking at the same phenomenon.
Well said, sir.
I just say it's a wave. That's now
Okay.
to throw another complication here. Of course, Bill Lucas is saying that particles are made of solitons, electromagnetic fields, and if Cornelius is here, he would definitely say that an electron is made out of a wave, so that there actually aren't any solid particles ever, right? Everything is made out of waves. So the electron hitting the detector, that was actually a wave hitting the detector, and the gamma ray is then obviously just a wave, right? Because everything's a wave. That's the other, just to represent the other side of the coin. Yeah. So let's summarize the possibilities here. So I just mentioned the possibility that everything is a wave. Electrons, protons, neutrons, they're actually not out of waves.
It was Sir William Bragg, by the way, that said that Mondays, Wednesdays. Sir William Bragg. I've just checked it up.
Uh-huh. And
Oopsie,
or the photon could be an actual.
Start that again, Franklin. You froze for a few minutes. We missed the first part of your statement, sir.
Oh, I was just kind of summarizing the possibility. So one possibility is that everything's a wave. All things that we call particles, including myself, is in fact some sort of localized waves. An electron is some kind of self-localized, self-reinforcing wave, or like Bill Lucas says, he called it a soliton of the electromagnetic field, whatever the heck that is, some particular geometric structure. And so that's one possibility. The other possibility is that light is actually a physical particle, like Draft's physics wants to say it's a specific clump. It travels from point A to point B, doesn't need any medium. It doesn't have any amplitude. It doesn't have any nodes. It just travels like a bullet. And the other possibility is that light is a wave in a medium. Of course, then the question is, what is the medium? And we have no evidence that this medium actually exists, at least none that the mainstream would take, right? So there's a problem with that. And then we have all these experiments which kind of confirm this thing that, it's a wave on Tuesday, Wednesday, and Thursday, and it's a particle on Fridays and Saturdays, whatever. And a lot of these experiments are fairly convincing to show that it's a wave or a particle, depending on what you're looking for or at. It has these characteristics. So, but like I said, I have my own personal belief. My own personal belief is that a photon is a wavelet in a medium. That's would be, and that is the equivalent of what draft science is calling his photon. But his blind spot is that he's not really taking into account radio waves, which travel in a completely different manner. And once again, I would have draft science go look at those original experiments that can detect the nodes in a traveling radio wave. And that to me is fairly convincing evidence that it couldn't possibly be like a little BB traveling from the antenna to the receiver, because if it was, there's no way there would be any kind of measurable difference in amplitude depending on how far away you are from the transmitter. That just
if I may jump in, this idea of the little BB for our particle model, it's like electrons, let's say in a conductor, may not move that much at all, but some movement will then repel additional electrons, and then this moves along the conductor in terms of carrying a current in the final analysis of a net transfer of electrons from one point to another in the conductor or in the medium. So this idea that even the electron has to be considered to be like a little BB is questionable, and I just throw that in for what it might be worth.
Yeah, then you have to go into the experiment where they basically proved that the electron was a little BB. You know, the famous experiment is a Crt experiment where they like have a CRT, and in that case, the electrons are literally little bullets, and they are literally transitioning from the emitter and actually physically hitting the screen. And they did things like they put a little Maltese cross in between there, and it created like a shadow. And you know, somehow that convinced people that the electrons were actual little particles that were traveling from the emitter to the screen. And
another way to look at that is that they're traveling through a media which has a definite density of energy quanta, which compose electrons and other particles, and this so-called little BB is being transferring energy through this medium, recreating itself as it goes.
Or it could just be a little BB.
Yeah.
I like to take the simplest possible explanation, but of course, then I have the problem of, well, what's that little BB? And it's like, I have to shrug my shoulders at that point. It's like, some people like Cornelius or Dr. Lucas will say that, you know, the electron is composed of like this or that. So they can go like one layer lower than, or you say, James, that, you know, the electron is actually the spot cube, and we have these little things moving around, you know, and so, you know, your theories can go that one level lower than mine. And so, you know, it's possible that, say, your theory, James, of the spot cubes could in fact be completely compatible with mine. But I think you have kind of a blind spot in that you try to use that for everything. It's like you try and make the proton out of, is also just a different kind of spot cube arrangement. But I think you would be correct to just stick with the electron being made out of your spot cube, and then making the proton out of like two positrons and an electron. And then, so you didn't actually have to go through the extra work of, I don't know, making a proton as being a distinct entity from the electron, as actually operating physically differently. I don't know what you think of that idea. I mean, do you think you went too far by uniquely identifying the proton as something different? Or, you know, could you have just simplified your theory by just saying, okay, that's a positron, that's an electron, proton composite of those things, and, you know, then it would be in total agreement with say, my theories.
Well, this is all laid out in various presentations that I've made in writing and video. My focus today is not on that work. It's more on just asking questions, and I'd like to build upon what Ian just said. I thought it was a very insightful comment that here in these sessions, there are many people, if I'm quoting him correctly, that are interested in seeing what is really in common going on that explains all of the data. Whereas in more conventional physics, this wave-particle duality is much more prominent. And whereas here, maybe we might be trying to look for where the common ground is in terms of what really is going on, rather than just saying it's this or it's that. Why don't we try to focus in on what it actually is? That was not necessarily the most articulate statement I've ever made. Excuse me for that. But I would like to try to build on what Ian was saying.
Yeah, I think as we're kind of free to propose whatever we want, and we can dig up the old arguments, rehash them. We may not get anywhere. It's kind of like arguing with your wife, It's like bring up all of this historical on you, right? It's like to bring up everything in the past that you ever did, as if it happened yesterday, right? And as dissidents, we can go ahead and do that, right? We can just dig up the past.
Well, with arguing with your wife, at least you know who's right. It's the wife.
Unfortunately, it's. No, we need to stand up. We're not always wrong, okay? We're not. We need to stand up and say, it's not our fault. It's not our fault, right? Now, if you want to have a little humor, you go look at my website. I've put up an audition for America's Got Talent, and it's a comedy act, and it's called, Victim of Divorce, for all those guys who have been divorced by their wife unilaterally. Right? It's like, I don't want a divorce, but it's like she's just driving off the cliff like Thelma and Louise. Just bat out of hell, want to get a divorce. That sort of thing. So I'm just trying to bring some awareness to this epidemic problem. So, but in any case, so that's not. I do notice we do have a fairly large set of comments going on here. So I see some new names here. We've got some guy named Funny Name. And, he's bringing up the point that if we do allow draft science to come on, and that it'll turn into a yelling and screaming match within 15 minutes. It's like, well, maybe. But if that happens, well, as moderator, I can, shut him down. But I think that he's a pretty reasonable guy. I don't think that it would turn into a screaming and yelling match. Certainly, I'm not going to be screaming and yelling.
By the way, Franklin, I was just wondering why he calls it draft science. Is it because he's putting it forward as a provisional position, or is he drafting some theory?
Well, I have no idea. You'd have to ask him, but clearly...
I thought he might have explained it in the presentation.
No, he's had that for a long time. He's got a real name too. But,
it seems to connote a sort of a provisional position that he's putting forward. I'm just giving you this as a draft, and I'm not sure if this is the final form. That's what I guessed. I may be wrong.
Let's see here. Yeah, he calls himself draft. See, he uses both draft physics in his URL, but his name says draft science presents physics the do-over. So. Now, he's a classic dissident who's trying to say, everything you've learned is wrong, right? And that's what I would say. Everything you've learned since about 1905 is wrong, right? Okay, all that stuff about electromagnetic fields, atoms, relativity, it's not a little bit wrong. It's completely backwards and wrong. That's what he and I would probably both assert, that all of that stuff is just.
So you'd imagine he ought to have said something like redraft science. If he wanted to say, look, everything in the last 100 years is wrong, and I'm just correcting you now. It's a redraft of science. But the fact that he says it's draft science would seem to indicate that he's really just going out into the air, and he's not sure of what he's doing, and he's not claiming that it's final. But I don't know. I'm just guessing, as I say.
Yeah, I wouldn't put too much into that. I mean, I put more emphasis on the theories he's trying to present, specifically light as strictly a particle phenomenon, right? And like I said, I don't think he's wrong, except that he doesn't know what his particle is made out of. And if you look closely enough, I would say his particle is made out of a wave that's shaped like a rod. That would be the only thing I would try and convince him of, right? Because otherwise, I agree with the behavior is generally as he says. It's quantized clump of energy, but it's different from a radio wave, which is not a quantized clump of energy. Now we do have some other comments from the Joker. Yes, we have celebrities in our presence. So now he brings up this light bending experiment, right? Although we haven't at all talked about light bending here. So I'm just going to guess that, and the guy's name is Gary, his real name, that he might, have some sort of problem with this. If light is a particle, then, why would it kind of bend in the presence of gravity? Although if it's a particle, that's easy, right? Of course, light is going to bend in the presence of gravity. The question would be, why does it not fall at 9.8 meters per second, like every other bit of matter that we have around here? If it was a particle like a BB, then it should be under the full force of gravity. And when I shine my light, it should fall at 9.8 meters per second, which is quite rapid. We could easily see that. But certainly light doesn't fall like that. I shine my light beam of light and it goes to the moon. I can shine lasers at the moon. It doesn't seem to be affected by gravity, not unless it's this gigantic, humongous, around a black hole kind of gravity. Then we certainly see these Einstein bending ring kind of things, and we can see behind the stars and all kinds of stuff like that. So I'm just kind of guessing. But that's more consistent with the idea that light is traveling as a wave, and that what's happened when light is bending around these gigantic stars, what you're seeing is actually a refraction effect, that the density of the medium increases around the stars, and it's just like the thick part of a lens, and the light bends when it hits that boundary, and that is what causes the light bending. So I would say that that is more consistent with the idea that there's a medium and that there's a light wave. I'm guessing. But he says that he was going to perform a light bending experiment, but he never did because he chickened out, or maybe because it's very difficult to do these experiments, or maybe because it's not right. I have no idea what he was going to propose, but like I said, if he thinks it's strictly a particle like an electron, then although there is this interesting thing that, you think an electron should also drop at 9.8 meters per second. Strangely enough, so there's very little actual experimental evidence on this, but from the people at Stanford Linear Accelerator, where they're shooting electrons across, 5 miles, I think as near as they can tell, gravity has no effect on electrons. It doesn't actually drag them down. If it did, they'd have to compensate for that, but they don't. So, individual electrons may be immune to gravity. But we know for a fact that neutrons are not immune to gravity. I mean, definitely you can send out a neutron, it will fall and it will bounce, and it bounces in a quantized manner. It can't bounce up at some arbitrary it has to bounce up at only certain fixed distances. But it definitely drops in the presence of gravity, as opposed to an electron, which may not drop in the presence of gravity. And that may be because gravity is created by dipole forces, and you must be a dipole in order to feel the effect of gravity. Because I think it's an electrostatic effect, but still, you think that an electron would be strongly attracted to the Earth if the Earth was a positively charged ball, like I think it is, So there still might be something screwed up about my theory that doesn't really account for the fact that gravity doesn't seem to have any effect on electrons. So maybe if that's true, then, well, maybe gravity doesn't have any effect on, I don't know, photons. Maybe, but I just thought I'd throw that in there. And then he said he started yelling and screaming at the guy who did the experiments, which ended up proving his theory wrong. Well, maybe. Once again, he does also understand this problem that nothing that any one dissident will say to another will ever convince them of anything, right? You can show them all the experiments in the world. It's like, if I go show Gary this experiment where I transmit like the triangle or sawtooth wave, and you go look at it, and hey, look, it's a sawtooth wave. He would not say, oh, well, I guess you're right, and it can't just be coming in clumps. He would never ever do that. He would say that your experiment is wrong, your experiment is biased, your experiment doesn't mean anything. He would never actually go and say, okay, my theory predicted the wrong thing, and this experiment shows that it's wrong. He would just never, ever do that. Now, I would kind of hope that if I were presented with evidence like that, someone showed some experiment which showed that there is absolutely no positrons or electrons, or I think that if you put a positron electron together, that will form a neutral particle which should be detected, right? So if someone did that experiment and they reacted a whole bunch of positrons, electrons, I'm predicting that the kinetic energy of that, basically are building neutrons, basically, that you should be able to effectively still detect the resultant particles. If someone actually did the experiment which convincingly showed that there is absolutely nothing left over from the collision, then I would hope I would have to say, okay, well, I guess that doesn't work and my entire theory is out the window, right? So I would hope that I would do that, but until someone does that, and I assure you, if someone does do that experiment, that they will find effectively a neutron being built out of positron electron annihilation. That I think that someone did that they would find it. But if they did that experiment and we found nothing, there's nothing coming out of these reactions, then I'd have to say, never mind. and go on my way and try and redesign my theory to not need that, right? But I don't know. I don't think Gary would. I think that you could present him all experiments up to yin yang, and he would talk his way out of it. So, what's he saying? So his theory violates the conservation of energy and momentum at every step, and he bans anyone who points it out to him after yelling and screaming at him first. Well, I don't know that that's true. Once again, I think the theory that light is a photon is correct. He just doesn't know what photon is. And everything that he says that photons do is correct. He just doesn't know what photon really is. Right? It's still a the action that we're seeing with it hitting, affecting electrons, and it's absolutely true, but it's because these medium particles are hitting the electron physically, like billiard balls. That is the action that's happening. And last week we talked about is it electromagnetic induction? Is it a magnetic field? Is it an electric field? I don't think it's any of those things. I don't think it's any of those things. And we shouldn't believe any of that stuff because it's never really been measured. Clearly things can be measured in an in-flight radio wave. Like I pointed out, you can detect the nodes in a radio wave. In fact, there's experiments where you take a candy bar and you stick it in a microwave. And because it's a resonant cavity, you can actually see the spots where it melts the chocolate. and you can actually measure the width, and from that you can calculate the speed of light, right? Because you can clearly detect that there is a wave-like nodes in that thing. So once again, that's another evidence that these things are waves, because you can see this direct distance versus energy output relationship, right? It's not BBs that hit everything, right? But I'm sure Gary would just completely deny that and, say that that's not relevant and not actually provide any actual argumentation as to why that's not relevant. Let's see. So the Joker's got all kinds of comments here. Says, I'm aware radio frequency experiment that Stephen Burrows performed, but I'm talking about a different experiment. One that's way simpler to understand and perform. Yeah, I don't know. It says his theory is so stupid it goes beyond violating conservation or blah, blah, blah. Although alone is enough to make someone a crank, his theory is way worse. Well, you can almost say that about almost any dissident in the world, I guess. That's why we're dissidents. He says, if his theory were true, the LIGO experiment would have never worked because the maxima of the laser light would constantly drift by entirely fast throughout the day due to the rotation of the Earth. Is that like presuming that it was particles? And that what the particles should always head in a straight line? And if the experiment is moving, then all of the beams, all the particles are going to like miss the target because we moved that much. Although I assure you, if that were the case, they would have designed the experiment to compensate for that. See, this is the thing about LIGO. LIGO is designed to eliminate every possible other signal source than the thing that they are actually looking for, which is this specific signature of two black holes colliding into each other. So they'll take every other signal they can possibly think of, the effect of the moon, the rotation of the Earth, the drift of the ether, and just null all of those things out. They don't care whether those things exist. So I don't think this is I'm just saying that this is not a valid argument, that it's like, even if it did drift, it's like they would have compensated for it. It's like, yeah, the Earth moves this much, so we're going to move our mirror over there to make sure it gets it and reflects it back. And I don't know if they care.
So presumably, just as in the GPS system, they've included these factors like for the Sagnac effect and so on for the Earth's rotation without sort of explicitly admitting it. But I haven't seen that for the LIGO, but presumably they have, as you say, Franklin.
I mean, for them to be able to measure the difference in the length of the arms of like less than a width of a proton, which is what they claim to do. I mean, I would claim that I could jump up and down in their visitor center and create a signal bigger than that, pretty much, right? But, they have ways of filtering. And I'm sure when I jump up and down in the visitor center that they actually see something in LIGO, right? But that's not the thing that they're looking for. And they're not looking for things that look like trucks driving in the nearby freeway. They know what that looks like. They get signals.
Well, that was the so-called justification for doubling the budget for erecting two stations in remote locations to eliminate any specific disturbance in one.
Yeah, exactly. That's really the only way you can do it. If someone flushes the toilet in the Hanford LIGO, that creates the exact same signal that they're looking for, right? And the only way that they can eliminate that is to make sure that they didn't see that same signal in the Livingston Observatory, spaced by the distance that they think the speed of light travels, because there's going to be something. So that's the only way you can eliminate the flushing of the toilet in the Hanford facility as being the thing that they're looking for, right?
Right.
So I assure you that if there was any other effect, and they would like completely ignore things like the MMX effect, the drift, the ether drift. They just, whatever that is, they're just going to cancel that out, right? Because that's not what they're looking for. All they're looking for is their little signal of that they have predicted in their supercomputer predictions to be two black holes colliding into each other, and that's all they're looking for. Just because otherwise, billions and billions of noise items come into LIGO like probably every second, and they have to throw them all out, right? There's some stories that they're getting this signal, and they found out it was actually a bird pecking away at the insulation on one of the lines.
And actually, these disturbances are probably of a much greater magnitude than the signal they're looking for. So the flushing the toilet is probably orders of magnitude greater than the effect from the collision of the black holes.
Yeah, exactly. It is. It's like, you walking around the business center, you are undoubtedly creating signals that are, probably 1,000 times greater than the signal that they're looking for, right? Something of that magnitude, right? If I want to drive them crazy, I'll just have my friend in Livingston. You just go knock on the outside vacuum tube at the same time while I'm doing it. This will drive them crazy, right? Yeah, at exactly 5 o'clock, start knocking on it, right? Okay. And that'll trigger exactly the same kind of signal that they're looking for. Because both of us are doing it kind of randomly, it's got to match up at some point, right? And then they'll announce that, yes, we've seen another black hole, right? It's like, okay. And then we'll say, no, you didn't see another black hole. That just me and my friend knocking on the vacuum tubes. So, because we know what you're looking for, so that's what we did. So what other things? The other scientists working on it would notice if the laser drifted by entire feet, it would be a massive conspiracy to hide that light travels in an absolute. Well, of course, it's a gigantic conspiracy that light travels in an absolute frame. And I mean, this is one thing I think I should research all of the things that they filter out in LIGO, and one of them has got to be the light traveling in an absolute frame. I bet you that you can detect the orbital motion of the Earth that they have molded out. That somewhere in there is the evidence that we're looking for, right? This for the absolute frame. It's in there. They just nulled it out, right? And so by mass computing, I mean hundreds of people hiding experimental results for hundreds of years. Well, yes, of course. As distance have been saying that the whole time, right? Or the other thing is that so far as getting the MMX time travel results, apparently the better vacuum you have, the less result there is. That you get results in air-filled interferometers, but not vacuum-filled ones, right? So by building the best vacuum possible, I mean, the vacuum in the LIGO is better than in outer space. That's how good the vacuum is. And that is probably one of the ways they eliminate this whole ether drift, the different speeds of light traveling in different arms. That's why they need the gigantic vacuum, because if it's anything less than gigantic vacuum, then you start seeing those effects. And you definitely don't want to see any effect that shows that the speed of light travels at different speeds when the Earth is pointed in different directions. That's not what you're looking for, right? So let's see here. He says, another example among hundreds is the laser reflectors on the surface of the moon. If light traveled in a God frame, the maxima of these lasers would drift enough that you couldn't bounce lasers off. Well, I don't know. Would it? Light travels pretty fast. And certainly, no matter how much drift is happening, you could always manage to hit the mirrors.
The point is whether in these determinations they actually introduce corrections, for such movement. I mean, for example, Al Kelly wrote to the then CCIR, the International Consultative Committee on Radio about their employing the effect of Sagnac effect in their calculations, but yet they claimed that it was a relativistic effect. It was allowing for special relativity. And he wrote to them, and he pointed out, he wrote to the chairman of the committee. This is about maybe 25 years ago, and he said, "Look, the relativistic effect would be 10,000 times smaller." And he said it's a Sagnac effect. So he got some sort of mealy-mouthed reply from the chairman saying, "Well, yes, you're not wrong. It could be said that, but it can also be derived by special relativity."
So, James, you did some work on those lunar ranging things, didn't you? Let's see. We got to unmute you there. So you got to unmute yourself there. We can't hear you.
Yes, I did, and that remains to be a very popular paper on my site.
So do you think that they are doing something weird to hide the fact that I don't know, that Gary is wrong or something about the light traveling, that the lasers would drift too much, that you couldn't bounce lasers off? I'm not exactly sure what he's saying there.
I'm not aware of any information that about that subject, about what drift there.
Yeah, well, I think he's just saying that that Gary's wrong.
Well, the observatories certainly believe that they are receiving signals back from the signals that they send, and the signals returning are within the ballpark, certainly, are very, very close to what would be expected with the speed of light, and so that the signals they're receiving, they believe, are reflections of the signals that they've sent. And but I leave all the technical stuff on that to them, those observatories. I mean, I've never worked at such an observatory to be privy to the details there.
Yeah, and then he commenting that the GPSs have to be adjusted, and that if Gary was correct, that this would be a conspiracy. And once again, I don't know. We have to call on Ronald Hatch, who's the expert on GPS. And I'm not sure that anything that Gary said would necessarily be in conflict with general relativity per se. Because I've got to kind of support Gary in the fact that that there are these photons, and that they do travel in clumps. They contain fixed amounts of energy. I mean, effectively, they are like bullets in the sense that they occupy a certain physical space as they travel. But that I would still say that they are a compression wave, traveling like a smoke ring through a medium of space, and that is what happens when it hits some other material object. It's made out of material. It hits material objects, and we see the energy being released. And I don't think that has anything to do with how that exactly works, because it, as a wave phenomenon and not a particle phenomenon, it would no longer be subject to the physics of particles. If that, maybe that's what he's complaining about, that as a particle it just can't do that. But if this photon is actually constructed out of waves, then all of those problems go away, right? It's maybe. He says, involving hundreds, thousands of engineers and scientists who work in these fields, he never has to answer to these things because he blocks comments, has refused to debate superhuman dance and hero. I have no idea what that means. But I don't know. He kind of debates me. So what he says, I can see that it's reasonable. So I still generally think he's a reasonable guy. I just got an incomplete picture of what's going on. This picture could be much more complete. So I'm saying, Gary, join me. Together, we will figure out the universe. Yeah.
How did you come across him? Was it just randomly, or were you referred to him, Franklin?
No, Gary kind of showed up in our science chats, right, and then got promptly banned. So, and like I said, he occasionally do this. He watches our show. Thanks, Gary. Thanks, Have Science for doing that. And he will occasionally make these videos, like I've been showing you, which are kind of responses. Daft Pines versus Franklin on polarization. That's cool because, he agrees it's an important topic that we should be discussing. And, he gets to bring up his ideas, and then I get to respond to his ideas. And he'll probably write another, response video to this. So, and I wait with bated breath to see, what does he think of my proposal that, he's absolutely correct, but his theory needs to go that one level deeper, which is my theory, right? Okay. And then together we can rule the universe together in agreement, right? Wouldn't that be something, right? But somehow I don't think so. I think he's going to stick with the particle, strictly particle, not in a medium, strictly a particle. Let's see here. We got a few more comments. We're almost getting to the end of here. Let's see. And there's also the images of light actually bending around massive galaxy. He has never explained these images, even when shown directly. Yeah, well, I gave you my explanation for why that happened, so I'm not sure what his thing is. Okay. See, he commits the fallacy of unfalsifiability because his paper claims that everything about his theory conforms to current science, same as religious fanatic saying evolution works with the Bible. I don't know. I think, James has said that. I've said that. Pretty much any dissident. Bill Lucas has said that. Pretty much, I think you can't be a dissident scientist unless you say that everything that I've ever seen matches with the results that matches with my theory, and it matches better than anybody else's theory, and you can't calculate this one obscure constant, and stuff like that. But once again, a lot of these theories do ground out to the existence of some postulated green fairy, let it be the electromagnetic field, let it be your ether ball, that's something called a fundamental particle, let it be a spot cube, always grounds out into something that we don't specifically know exists. And except for my theory, which grounds out at the electron, right? That's where my theory grounds out at. But I don't know what an electron is. Now, these other theories may go a little bit deeper and say what electron is, but I still haven't seen any convincing theory that actually seems to make any sense, right? It's like it could be these things, but there's, just zero experimental evidence, and there's no way you can even do experiments. It's like, string theory. It's like, sure, it makes perfect sense on the blackboard, but there is no experimental evidence you could ever do to show that those strings exist, right? And I think that's just false. As a physicalist, I have to fall back on things that I can, feel and see, and I can feel and see electrons. So I'm happy to base all my theories on the existence of the electron and not some green fairy that I just, have to make up. The power of the green fairy is that it can do anything you want, right? It's your fairy. It can do this, whatever. So that would be my little soapbox on falsibility, right? It's like, yeah, you can't falsify the theory. There's no experiment you can do to falsify it. It doesn't mean it's wrong, but it just means it's probably wrong. It's probably wrong. In order to be convincing, you actually have to come up with predict a new result that cannot be predicted by any other theory, right? That is when you get to the convincing experiments, because You can always back predict any existing experiment. Take any experiment that's been done, you can shoehorn it into your theory. It can be done, right? It's called, deep, ad hoc additions. You can always do that. What's harder and more convincing is that, I've predicted that if you react a positron and electron, and if you look for the neutron, you will find it, right? Now that's, if they do, that's not a result that can be accepted by the mainstream, who thinks that it's completely annihilated, right? That's just, I've made that prediction. My prediction is if someone actually goes and looks for it, they will find it, right? So, and that would be the physical evidence that, my particle, the positive actually exists. I mean, it's actually a neutron, really. So it's already been discovered. I'm not using or relying on anything like a photon that we don't know actually exists. And I explained photons in terms of those basic positrons and electrons. So photons are a composite particle, not a fundamental particle like Gary might say it is, right? And that's falsifiable, right? So let's see here. So we agree he's a lunatic, and when you draw the force arrows, they're not force arrows, they're like physics teachers draw. He thinks they're physical force objects in a physical particulate. Well, does he think it's a particulate or not? I don't think he's a lunatic any more than I do. I just think he has quite possibly an incomplete picture. And he's pointing out all the screwball things of mainstream. He's not wrong there. He's saying not a property of matter, but matter itself. He's confused of. Well, and Musera is asking, who are we talking about? We're talking about this guy, Gary, who runs this draftphysics.com. He calls himself Draft Science, and he's responding to one of my videos here when I try to explain polarization. We haven't even gotten to too much of that polarization stuff yet. Let's see here. Yeah, and you got the answer from Funny Name about who this guy is. Who got banned, and he's saying, Draft Science, I know you're watching. And when we trace the phone number, it's right next door. No, don't be shy. Want me to talk about Malcolm? Will you jump out from cowardly shadows then? Well, I don't know. I think this guy, the Joker's got something. He's out to get you, Gary. Let's see here. And it says, I wouldn't give attention to Eddie Craze and has gotten Franklin to give him. Well, I'm just as equivalently bringing attention to my own theories, which kind of conflict what he's, well, like I said, doesn't actually conflict. He's just like completely ignoring the nature of the radio waves as being different. He said, I don't think anything that he said is necessarily really wrong. It's just, it's limited. It doesn't apply to radio waves, right? It says, how come a wave is not a particle? For me, even a wave is a particle of some kind. What is the definition of a particle? Well, obviously, as James explained, waves are made of particles, and the things that's transferring the energy is, in fact, the collision of one particle to another, right? So what is the definition of a particle? I would say the definition of the particle is an electron or a positron. Whatever those things are, those are particles, right? That's how I'm going to choose to define it, right? Whatever that thing we see, electron, that's a particle. And everything in the world is made out of electrons and positrons. So anything that's made out of positron, electron, like I think proton is made out of, those are particles too. But I'm just going to retreat back to my basic postulate, which is the electron exists, it's a particle. Just, that's it. Whatever you think is a particle, it's got to be made out of positrons and electrons. That's it, right? I'm not even going to tell you what the physical properties of a particle are. I'm just going to tell you what an example of a particle is. In fact, the only particle that actually exists in the entire universe is the electron. So we'll just make those equivalent. Electron, particle, right? And let's see, a wave is a thing is a particle is a thing. Why not? Well, yeah, they're all things, right? But you got to get the hierarchy right? I prefer to start the hierarchy with the particle as the electron. You fill all the space with electrons, you've got a medium. And then you can have a wave in a medium. It can have different levels of compression and rarefication. That's what a wave is. I think that makes the most sense, I think. Let's see, we've got Bill is saying some things about sound waves are longitudinal wave, radio waves are transverse wave. They are very different. And to Bill Lucas, as I prove it, show me the transverse wave in a radio wave, right? Show me the 4 things that it must have. It must have independent magnetic field. It must have independently measurable magnetic field. It must be shown that those 2 fields are at right angles to each other, and it must be shown that they are in phase. That is what the EM wave equation absolutely demands. Now, there were some arguments that, oh, Franklin, you can never measure that, right? It's like you can never, in which case I would say that that's even a worse situation. You have a theory which can't possibly be proven at all experimentally. That is the worst situation you could possibly be in. It's like string theory. It's like, yeah, we can't, there's not a single experiment we could possibly do to prove this. Now, why should we believe in it? Why should anyone believe in this if you've got a theory which can't be experimentally proven at all, not even theoretically, right?
Well, as I've pointed out on previous occasions, you can measure the effects of these electric and magnetic fields.
Well, certainly you can, but it's just an voltage measured at the receiver. I mean, we have no idea. We only see it when it actually hits the antenna.
No, also in regard to the spectra, the effects of the electric and magnetic fields on spectra. If you have a spectrum through which the radio wave is moving, you can actually measure its effects.
Really? I didn't heard that. I mean, I would consider that a valid proof that if.
Okay, I thought you might just explain it another way. So if you look at things,
no, I mean, if you were to transmit a radio wave through some, like you're generating, like you have a plasma tube and you're shooting electricity through it, and you're generating, spectra, and you could show that during the transmission of the radio wave, when you turn that thing on, that it actually affects the electrons in a specifically either a magnetic or an electric way, or it would have to actually do it both. And then you would have to be able to measure the 4 properties that I said, which is that there's an independent electric field, there's an independent magnetic field. Now, theoretically, Spectra could measure that, and you could measure the angle at which they occur, which you could show it's at 90 degrees. So, if you could do that, I would accept that as proof that it's actually traveling with electric and magnetic field. Now, so if you can find that, then please send it to me. I'd love to take a look at it.
I don't know if these experiments have actually been done. I do know that you can measure the effects of a magnetic field and an electric field on such a discharge system producing a spectrum. And I think maybe some experiments have been done, but you have to do a bit of research to be able to get a significant amount to convince you, I suppose.
Well, like I said, I would think that if I were presented with, evidence like that, then I would have to hopefully say, okay, you've proven your point. I'm wrong. The radio wave does travel with an electric and magnetic field, right? It's like, okay, you measured it. It's at 90 degrees, right? I can't. But I'm guessing that doesn't happen. I'm guessing it just totally doesn't happen. Right? Do the experiment. It's like, I assure you, you will not find it to be true. And you can send radio waves through spectra being generated, and they'll see absolutely nothing. Just nothing. Okay, that's my prediction. You see nothing. But that would be a good suggestion for how you might actually go about doing it, right? So someone should do it, right? So somebody, that's what I keep on hoping for, that, my stuff has been out for 15 years, and it's like, no one cares. No one, no one.
But you also say that in the vicinity of a high power transmitter broadcasting system, you wouldn't measure any electric or magnetic field. So, I think with respect, perhaps you have to marshal the experimental evidence as well. I mean, you throw out these ideas. I certainly believe that you wouldn't measure any field. But if you do, well, I have to think again. But I mean, the onus is as much on you to produce your evidence, I would submit. In regard,
I need an experimentalist to take my side is what I need. But no one cares. I know people are reading my stuff. I mean, I can track down who is actually hitting my website, and it's like universities and guys like that. People who should know are reading my stuff, and nobody writes, no one calls. The Nobel Prize Committee has still not knocked on my door. It's frustrating. So, but I need to stop wasting my time. I really need to walk myself down to the University of Washington and start talking to the actual physicists and try and ask them the questions they can't answer, and get the experimentalist to confirm or deny my my thing. I mean, that's a very basic thing. It's like I should be able to ask the guy in the University of Washington, so can you find me these 4 things, right? Where's the papers that show me these 4? If not, then can we get some grad student to go find these things, right? It's like, if it's never been done, I think that would be very interesting, right? Apparently have not been done. Apparently, if they look, I'm guessing they're not going to find anything, no matter how hard they look. So, but we're at the end of the time. I see we do have one little funny comment here, so I'll put that up. It says, arguing with women is like arguing with Gary. If your wife is right, she sticks to her point till grim death. If she's wrong, she brings up stuff that has nothing to do with the argument to derail. Yeah, that's exactly what what people like to argue with Harry. He argues exactly the same way. If I present a point that he can't possibly deny, then he just brings up some other completely unrelated point, and we're just not sticking to the topic. So, but that will do it for today's topic. So, Gary, so I hope you're watching, and if you want to do another response, please do. And that will do it for this week's episode. So thanks for everyone showing up, and hopefully see you next week.